Welcome back. In this video, we'll run through several examples of machine learning in Python. We'll start with linear regression. We'll use familiar data sets so you can compare code using Python with previous code we've used with R. All right, I have a link for where you can find all our data sets, and I'm going to use our Boston data set here. So all that's really changed is the syntax. We use a pandas.readCSV to read it in. We have a head method we can apply to a data frame, a shape method as well. I've subsetted just the rooms and median home value, and this describe is a little bit like summary in R. So we get all these summary statistics for the columns that I selected. We can make a plot. Here I have rooms, number of rooms in a home on the x-axis and the median home value on the y-axis. And notice all these dots. In this data set, it appears that the upper limit was decided to be 50, so any median home value above 50 was just encoded as 50. Next, we'll use the built-in train test split method to give us 20% in test, and we'll need a random state here. I've included the imports near where they're used so that you can see very easily what you have to import to do something. So in other words, to do linear regression, this is our import. And then we actually train with the .fit method. Here are our parameters. You can extract out of what it learned the intercepts and the coefficient. And there's a built-in predict function as well. sklearn has many metrics, so we'll look at mean squared error and an R2 score. And finally here I've plotted on the x-axis the true values and on the y-axis the predictions. And you can see how well they line up or don't line up for this regression. In linear regression in R, when we built our model, we got a lot of statistics about the coefficients. Their standard error, t-values, p-values, and so forth. And we also got a lot of summary statistics about the model overall and how well it fit the data. We don't have that in Python. We also don't have the plots of the residuals that we could do in R. So overall, I would say that the R environment for linear regression is a bit more comprehensive than sklearn. But if you just want to perform the linear regression, you can get that done in sklearn. For logistic regression, we'll use the Titanic data, and we just want to use certain columns, so we can use this use columns parameter and look at the first few rows. 3 of these columns need to be a factor, so we can update them as type category.cat codes to give an integer representation for the categorical data. We'll count how many are missing. We'll use NumPy to calculate the mean and fill the age NAs in place with the mean. We'll do a train test split, import logistic regression, fit the model, and then get a score on the model fit, which is an accuracy score of 0.78. We'll make predictions and print out several metrics: accuracy, precision, recall, and F1 score. We can print out a confusion matrix as well. There are a lot of parameters that we can change with logistic regression. Here's just one example of making the class weight be balanced between the 2 classes of survived and not survived. And then run that again, and then we see that our accuracy is the same. Our precision went down, and our recall went up. The F1 score is a geometric mean between precision and recall, and we see that we have a better F1 score with the second model. As we noticed in linear regression, the summary of the logistic regression in R, we don't have any comparable functionality in sklearn. So I would say that most data scientists would probably prefer R for both linear regression and logistic regression because of all that statistical analysis that R provides. Let's run the same data through naive Bayes. First, we'll use the multinomial naive Bayes algorithm, make predictions, and we see that our accuracy is quite a bit lower. One new thing in this notebook is the classification report, which breaks down by class, precision, recall, and F1 score, also giving accuracy as well as a macro and weighted average. So we didn't get very good results with the multinomial algorithm. The multinomial is best for discrete predictors that have multiple levels, whereas the Bernoulli is best for binary predictors. There's also a Gaussian naive Bayes for quantitative predictors. We kind of have a mix of predictors in this particular data set. Just for comparison, let's try the Bernoulli naive Bayes algorithm. And we see that we did much better with this one, but still not quite as good as logistic regression. Comparing naive Bayes in sklearn with R. One thing that we're missing here is the ability to extract the learned probabilities from the model. That's very easy in R. But sklearn has the several different models, the Bernoulli, multinomial, and Gaussian here. I have links to the documentation that make it a much more flexible algorithm. Let's look at KNN for classification first. We import the K-neighbors classifier. To set up the classifier, we need to specify the K, the number of neighbors, and then we can fit. As you can see, there's some other parameters we could change as well. Our accuracy is 0.77, and here is the classification report. Let's look at a regression example real quick. On the Boston housing, we do the same pre-processing. For regression, we'll import the K-neighbors regressor. In this case, our neighbors will be 3. We'll make our predictions. We'll look at mean squared error and an R2 score. Didn't do that well compared to linear regression, so we'll scale it. After scaling, we got much better results, and we also improved over linear regression as well. Comparing this with R, it was easier in R to do the cross-validation to determine the best K. In the chapter, I have some code about creating a pipeline that would be one way to try various values of K. The last algorithm we'll look at in this video is decision tree. So we're going to import decision tree classifier, and then from then on it runs pretty much like the other algorithms we've seen. We can also try the random forest, which didn't vastly outperform the decision tree in this case. In all of these notebooks, I've been running one algorithm at a time, mainly for reference purposes, so you can see exactly how to run one algorithm. Let's look at how to run a bunch of them. I have all my imports here. I'm going to load and pre-process my data. Then I'm going to set up my models, logistic regression, naive Bayes, KNN, and decision trees. Then I will iterate through all of those models, collecting the accuracies, and then printing them out. This is one way to very concisely show the results of many models. sklearn also has a pipeline function that can also automate this. In a separate video, we'll look at using sklearn for neural networks, and we'll also look at using the Keras package for deep learning.